Okay, so my name is Mara and I'm going to give a quick example of a random walker, and this is very much like midterm 3, but I think it's helpful to explain kind of where the terms come from, because at least I know for me it wasn't clear. So here we go. So we have John, and John has a 1/6 probability of moving to the right, a 1/3 probability of moving to the left, and a 1/2 probability of just staying still. So we know that his probability of going somewhere new to the next spot is 1/6 the probability that he's coming from the left. Because remember, if he's moving here and he's here in time n at spot time n plus 1, it means that at time n he was at the left. So he was in that left spot at time n. Plus 1/3 probability that he's coming from the right, that he's moving left. Kind of confusing, so it's good to really think through what that means. And then a 1/2 probability that he's just coming from that exact same spot. So when we expand this out, this is how we do it. So we look at this px of t plus tau dt of px of t, and we expand each term by itself. Now, we know that this is the Taylor series expansion for this term, px of t minus a, up to 2 terms, which is, well, 3 terms, which is all that we really care about at the moment. And the thing is, when he stays in the same spot, when he has a probability, this a becomes 0, so all these a's become 0. So for the pink, which is what they stays in the same spot, we only end up with this one term, and that's a 1/2 probability that he stays in the same spot. Now for the 1/6 probability he moves to the right, we expand this out. We have 1/6 px of t minus a dx px t, a squared over 2, etc. So this is pretty normal. We know how to get this. And then again, we do the same thing for 1/3. Now notice what's very important is this minus sign right here. And this comes from the fact this t minus a, right? And that's because he's coming from the left to the right if he's moving to this spot at time n plus 1. But if for moving leftward, which is coming from the right, this is at a t plus a is his position. So this right here is a plus sign. I can make it even more clear. And this is a minus sign. And that's going to make all the difference when you go into the algebra, so you really want to make sure that you have that right. Okay, so if we kind of rearrange these terms and we group all the just px of t and t's together, we see this. We get 1/2 px of t plus 1/6 px t plus 1/3 px t plus stuff, which we'll figure out later. And this is important because this should make a lot of sense to us. Obviously, our probabilities are going to add up to 100%, so all of these are going to add up to 1. And this px of t cancels over here with this one. Boom. So those are gone, and we're left with just this and all this stuff that we're then going to figure out. So this is what we're left with. We have tau dt px t, and we have these terms, which I've grouped according to which derivative they are, right? So we have the first x derivative of px t, and then over here the second ones. So we get a negative a over 6 contributing from him moving right, and an a over 3 contributing from him moving left, and then an a squared over 12 from him moving right, and an a squared over 6 for him moving left. And again, just to show where this comes from, we have this 1/6 here, and this is the a. So that's where, for example, the negative a over 6 comes from down here. And that's the same for all the terms. We're just multiplying out. Now when we group these terms together, we're left with a over 6, dx px t, and a squared over 4, dxx px t. Now, it could be a little confusing to you kind of where this tau comes in, but it's important to realize it's multiplying over here. So in order to just be left with dt px t on this side, we have to bring this tau over and divide these terms by it. So we're left with a over 6 tau dx px t and a squared over 4 tau dxx px t. So don't forget about that tau. You can't just kind of plop it in there. You need to know that it's coming from this side of the equation, and that's the important part. So when we have our equation in this form, it's really easy because these two coefficients are our drift velocity and our diffusion constant. So really easily we can see that this a squared over 4 tau is the diffusion constant for this setup, and that this a over 6 tau is the drift velocity. Now we know drift velocity is left because it's positive. And remember, that may be kind of contrary to what you're thinking, but you have to remember that if he's moving left, kind of he's coming from the right. And so this drift velocity is going to the left. And this is in contrary to the example in the midterm when we had a negative coefficient up here, and we knew it was going to the right. So this is just an example, once again, of how kind of we can figure out exactly what the drift velocity and the diffusion constant are for any sort of random walker situation. Thanks.